Hi all, welcome to our class. Today let us start new topic. The topic is circles. So here I have drawn three different figures, figure 1, figure 2 and figure 3. Three figures are there, 1, 2 and 3. Three figures are there, 1, 2 and 3. So our topic is circles. So here a circle and a line. Here also a circle and a line. Here also a circle and also a line. So in first circle, then a line PQ. This line not touching the circle, which means not intersecting. Not intersect any points. So it's non-intersecting line. So circle and a line. In first figure, non-intersecting line. Non-intersecting line. Non-intersecting line. In second figure, here circle, a line. So 2 points A and B. This line intersect at 2 points. One here. Other point B. So line PQ intersect the circle at 2 distinct points A and B. So there is a line and a circle. That line intersect the circle at 2 distinct points A and B. So then this is called PQ is called secant. Then this line intersecting at 2 points is known as secant. Line intersecting at 2 points known as secant. In third figure, there is a circle and a line. This line meets at only 1 point. The line intersects at only 1 point. Point is A. At A, the line intersecting the circle. So we can say that this line PQ is known as tangent. This line PQ is known as tangent. Very important concept, tangent. So tangent means a tangent to a circle. PQ is known as a tangent. So a tangent to a circle is a line that intersects the circle at only 1 point. Tangent to a circle means a line that intersects the circle only at 1 point is known as tangent. So here 2 distinct point meeting. So secant, this is non-intersecting line. So non-intersecting line, this is secant and touching only 1 point, that is known as tangent. So tangent to a circle is a line that intersects the circle at only 1 point. Then one more concept. There is only one tangent at a point of the circle. So here only one tangent at a point. When we consider point A, here is only one tangent. We cannot draw one more tangent there. At a point, there is only one tangent. So there is only one tangent at a point of the circle. So have non-intersecting line, secant and tangent. Let us discuss one theorem. The tangent at any point of a circle is perpendicular to the radius through the point of contact. This is the theorem. The theorem states that the tangent at any point of a circle. So consider a point P. So we draw a tangent. Tangent means intersecting at 1 point. That is called tangent. So the tangent at any point of a circle is perpendicular to the radius. Here radius OP is the radius. So this is the tangent and this is OP is the radius. So the tangent at any point of a circle is perpendicular to the radius through the point of contact. So P is the point of contact, OP is the radius, XY is the tangent. So this radius OP and the tangent XY are perpendicular. So we have to prove this theorem, very important theorem. So the tangent at any point of a circle is perpendicular to the radius through the point of contact. First, we can write the given things. This is the format. First, we have to write the given things. A circle having O as a center. Circle O as a center. XY is the tangent to the circle which meet the circle at P. So, we have written the given things. Then, to prove, radius is perpendicular to the tangent at a point of contact. That is, OP is perpendicular to XY. That we have to prove. OP, radius is OP is perpendicular to tangent. So, tangent and radius are perpendicular. So, OP perpendicular to XY. Then we have to do some construction. Let us take a point Q. In this tangent, I consider a point Q. In this line, in this tangent, I take one point Q. Then, which meets circle at a point A. Which meets circle at a point A. So, I consider this point as A, which means consider at a point A, join OQ. We joined OQ. These are the constructions. So, let us move on to the proof. We have to prove OP is perpendicular to XY. So, this is the point O. This is a line. So, we have to say that this OP, that is the radius, is perpendicular to this tangent. So, we know distance between one point and a line. We know the distance, which means the shortest distance. That is the perpendicular. When we consider the distance, this is the perpendicular. That is the height. That is the perpendicular distance is called height. So, this is the circle, radius, tangent. We are going to prove that this OP is perpendicular to XY. Let us move on to the proof. We have given things, all these things we have to write. We have to write OA less than OQ. OA less than OQ. By the construction, we can easily write OA less than OQ. What is OA? This is OA and this is the OQ. That is, from this point, Q is outside the circle. Q, since Q is outside the circle. Outside the circle. And A is the point on the circle. So, obviously, OA less than OQ. Q is outside the circle. So, OA less than OQ. But, we know OP is the radius and OA is also radius. So, we can write OP is equal to OA. OP is equal to OA, which means radius of the circle. Radius of the circle. So, first we took OA and OQ. From the figure itself, we can say that OA less than OQ. OQ is bigger than OA. So, OA less than OQ. But OA and OP are radius. So, OP is equal to OA. Therefore, we can say that OP less than OQ. OP less than OQ. OP less than OQ. Or OP is the shortest distance from O to the tangent XY. So, OP is the shortest distance. OP is the shortest distance. OP is the shortest distance from point O. From point O. OP is the shortest distance from the point O to the tangent XY. So, OP is the shortest distance. So, OP is the shortest distance. We take a point Q. So, if we take Q anywhere outside the circle, so that will be OQ will be greater than OP. This is the shortest distance. So, OP is the shortest distance. OP less than OQ. If Q is here, then also we can say that OP less than OQ. If anywhere outside the circle, only one point P, the circle, tangent meet the circle, then OP is the shortest distance. All other distances are larger than OP. So OP is the shortest distance from point O to the circle XY. So we can say that shortest distance, all distance from any point to any line is perpendicular is the shortest distance. Let us write all distances from any point to any line is perpendicular is the shortest distance. So from a point to a line, the shortest distance is perpendicular distance. So we have OP is the shortest distance. So all distance from any point to any line is perpendicular is the shortest distance. So we have OP is the shortest distance. So we can say that OP is perpendicular to XY. Therefore, OP is perpendicular to XY. OP is perpendicular to XY. So hence radius, OP is radius perpendicular to tangent at the point of contact. So radius perpendicular to the tangent through that point. So radius is perpendicular to the tangent. Let us discuss another theorem. The theorem states that the lengths of tangents drawn from an external point to a circle are equal. Before that, we have to say one thing. From a circle, if there is a circle, from an external point P, we can draw exactly two tangents through to a circle. Two tangents we can draw to that circle. From a point outside the circle, exactly two tangents to a circle through a point lying outside the circle. So a point outside the circle we can PT1, PT2, two tangents we can draw from a point outside the circle. So we are going to study this theorem. The theorem states that the length of tangents drawn from an external point to a circle are equal. The theorem states that, so a circle is there. From a point I am drawing two tangents P. This point is Q and this point we can draw two tangents. So we have to prove these two tangents are equal. PQ is equal to PM. That is our theorem. We have to prove PQ is equal to PM. So our theorem states that the lengths of tangents drawn from an external point to a circle are equal. So we have to write the given things. So first we have to draw the figure. So this is our figure. From a point we are going to draw two tangents P, Q, R, two tangents P, Q, R. This is the center or is the center of the circle. We have to prove PQ is equal to PM. So let us move on to the proof. Before that, given things we have to write. What we have to write? O is a circle. From a point P outside circle two tangents PQ and PR. We have drawn two tangents PQ and PR to the circle. Then to prove PQ is equal to PR. We have to prove PQ is equal to PR. We have to prove PQ is equal to PR. Then construction join OP. Construction, next heading is construction join OP. So we have to join this OP. So this OQ and OR are the radius. We can easily understand that OQ and OR, since O is the radius, OQ and OR are the radius. So OP, we have construction OP join OP. We are joining P and the point O. So let us move on to the proof. Very simple proof and very important proof. So OQ is the radius and PQ is the tangent. We know OQ is the radius and PQ is the tangent. So we have studied radius is perpendicular to the tangent. So we can say that angle PQO equal to 90 degree. Reason is that radius perpendicular to tangent. Last theorem we have studied radius perpendicular to the tangent. So angle PQO is equal to 90 degree. So angle PQO is equal to 90 degree. Similarly, PRO, angle PRO. This is the radius, this is also tangent. So this is a 90 degree. Radius perpendicular to tangent. So angle PRO is equal to 90 degree. The same reason. Radius is perpendicular to tangent. Then consider these two triangles. Let us consider these two triangles. In these two triangles, we can say that PO is equal to PO. PO is equal to PO. That is, PO is equal to PO. The reason is that common. PO is equal to PO. So angle PQO is equal to angle PRO is 90 degree. Angle PO is equal to side PO is equal to PO common. Then OQ is equal to OR. OQ is equal to OR. Both the radius of the circle are equal. So radius of the circle. So OQ is equal to OR. So these two triangles are congruent. Triangle PQO and triangle PRO are congruent. Triangle PQO congruent to triangle PRO. Reason is that both are 90 degree. Then right triangles. Once this side is equal, then OQ is equal to OR. That is, these two sides also equal. So this is 90 degree. So the angle opposite 90 degree is hypotenuse. Here 90 degree, angle opposite to 90 degree hypotenuse. So PO is the hypotenuse. So PO equal to PO, hypotenuse are equal. Then one side OQ is equal to OR, radius are equal. Both are 90 degree. So triangle PQO congruent to triangle PRO. The reason is that RHS congruent criteria. By RHS congruent criteria. Therefore, we can say that PQ is equal to PR. That is CPCT. So, side PQ is equal to PR. So, PQ is tangent. PR is also tangent. So, tangent from an external point to a circle are equal. So, from outside a circle, we can draw two tangents. These two tangents are equal.